Hi class, this video is on topic C8, magnetic force on a moving charge and magnetic force on a conductor. We have talked about this magnetic force qualitatively through right-hand rules, but now we're going to talk about it quantitatively. And charged particles entering a magnetic field and there's a resulting force on them are involved in a large Hadron Collider, which is a famous particle accelerator that we will learn more about in the next lesson. So just recap that a magnetic field is the space surrounding a magnet in which a magnetic force can be detected. Field lines indicate the strength and direction of the magnetic force. How do we quantify this strength? So if you think back to the previous two chapters, we have a gravitational field strength, which gives an idea of how massive the planet is, or how close you are to the planet's surface. We have electric field strength, which gives you a strength in terms of the electric fields chapter, but we don't have a magnetic field strength yet. So let's define capital B as the magnetic field strength, and it has SI units of Tesla. So 1 Tesla, capital T, is 1 kilograms per coulomb second. Just like the other field strengths, small g and epsilon, capital B is a vector quantity, so we put a vector arrow on it if we are formally stating it. And if you don't include it, then you're just talking about the magnitude of the field strength. The magnetic field strength near Earth's surface is 50 times 10 to the minus 5 Tesla, and an MRI has a field strength of 7 Tesla. The direction of the magnetic field, remember that we have right-hand rule number 1 for the direction of, giving us the direction of the magnetic field lines around a straight conducting wire. So pause this video right now and hold your hand up like that just to really reinforce it. Do it kinesthetically. And then right-hand rule number 2, so try it for right-hand rule number 2. This is for the north and south poles that are created as if a coil is a bar magnet. So when there's a current carrying coil and we can create sort of a bar magnet out of it, hold your hand like that. So notice that the actual shape of your hand does not change from right-hand rule number 1 or 2. Just if you're following these diagrams, you're just going to rotate at the wrist, or I guess at the elbow. We also have right-hand rule number 3, which we're going to get to in a second. But discovering that force, so right-hand rule number 1 and 2, we are talking about a current direction, conventional current direction, and the magnetic field strength, magnetic field lines direction. So we've got the current and the magnet. Those are the two things in both of these right-hand rules. But recall that right-hand rule number 3 has the current, the direction of the current, the direction of the magnet, and the direction of force. So where did that force come from? Recall from grade 11, you talked about Ampere discovering that 2 current-carrying wires, there will be an attractive or repulsive force on 2 current-carrying parallel wires. And this is because the interaction of the magnetic field lines that the current-carrying wires create. So in this particular situation, if the current-carrying wire is going opposite current direction, the magnetic field lines, in this case, are clockwise and counterclockwise, such that they point in the same direction here, and that causes repulsion. So he showed that there could be a force on a current carrying wire, and this led to the motor principle. So if we have a current that is pointing, this X means that it's pointing into the page. If we have that current carrying wire in the presence of a magnetic field, there will be a force created on this. Pause this video right now. See if you remember what this right-hand rule is that will allow the determination of the direction of the force. So even if you don't remember the right-hand rule, you might already see, well, this would be repulsion on this side and this would be attraction on this side. So overall the wire wants to go downwards, there is a magnetic force on this wire. When it is carrying current that direction, so into the page, when the magnetic field direction is this way, the magnetic force will be down. So if you look at the motor principle, it says a current carrying conductor that cuts across an external magnetic field experiences a force perpendicular to both magnetic field and the direction of the electric current. So the magnetic field is down and the current is out of the page. So if this was an arrow coming out at you and draw a line from north to south, those two lines are 90 degrees to each other. Well, the force is also in 3D space 90 degrees to those already 90 degree lines. So if you have a line up and down and a line out and in, what's 90 degrees to that? Well, it could be to the right or to the left. So how do we know if it's right or left? We actually need right-hand rule number 3, or you need to analyze the magnetic field lines here. So we have open your curled fingers so that you can use your palm as one of the variables. Our thumb is going to be conventional current. Our fingers, so from wrist to fingertips, or what are they called? Fingernails, wrist to fingernails, that's the direction of the magnetic field lines, north to south. So north at your wrist, south towards your fingernails. And then your palm shows the direction of the force. So this is this magnetic force that this whole lesson is on. So you are going to be practicing this a lot when you do the practice questions. What is the magnitude of that force? So the right-hand rule number 3 is your go-to to figure out the direction. But the magnitude you get by using this formula. A magnetic field exists a force on a moving charged particle. The magnitude of the force on the charge is calculated by QVB sine theta. Little q is charge on the particle in coulombs. V is the magnitude of the velocity of the particle in meters per second squared. So that should be meters per second, or sorry, meters per second. That should be meters per second there. And then B, our magnetic field strength variable, that is in units of Tesla. And then the angle between velocity and B. So in all examples so far from grade 11, velocity and magnetic field, or sorry, the direction of the current and the direction of the magnetic field lines have been oriented 90 degrees to each other, sort of to just like dip our toes in the water to kind of understand a simple example. And in fact, this force is the greatest force. The force is optimized when theta is 90. So we just ignored this part last year, but now we have to recognize that the current may not be in the direction of, 90 degrees to the magnetic field lines. So I'll show you what I mean by that through diagrams, which hopefully will make more sense than my words. But this is the equation that we follow to get the magnitude of the force. We know that force is actually a vector, so when you give your final answer for force, you will have to slap on a direction to the end after the number with sig figs and the unit, and then you'll add a direction using your right-hand rule number 3. What is the direction of the force? Well, use right-hand rule number 3. Now, since we are talking about conventional current, that thumb is actually, you could think of it, it's the velocity of the positive charge. We know that in real circuits, it's electrons that move, and conventional current is all backwards, but we will use this problem for like a moving proton as well. We use this rule for a moving proton. We had conventional current because we know in a wire there are moving charges, but we're going to be able to use this equation for magnetic force, even if it's just a single electron or even a single proton. If we had a negative charge moving, like an electron, we would have to flip our answer from this. So yeah, just rewrite it. This is rewriting the right-hand rule number 3, but it's the grade 12 version. So now your fingers point in the direction of B, magnetic field strength, or sorry, magnetic field. And then the thumb points in the direction of that velocity vector. And then the palm shows the direction of the magnetic force. Notice if the charge is negative, the direction of the magnetic force is the opposite. So if you're talking about a negative force, that would be down here. That would be for if it was like an electron moving instead of a proton. Okay, what's so special about magnetic force? I love this picture goes with any meme here. Like it's almost summer, or I feel special. So the magnetic force is special because the magnetic force depends on the velocity of the charged particle. Why is that so interesting? Well, if you think about it, like your mass, when you're talking about gravitational, the force of gravity and the gravitational field strength, that ball that you hold up, it doesn't matter if that ball is moving or not. So the velocity of the ball that you hold up does not determine the force of gravity. So, and same thing with our electric force. Those two charges, those 2-point charges using Coulomb's law, there was nothing, the motion of the objects creating the field didn't come into play when you're calculating those forces. So it is different that we have velocity in the equation. Direction of the force is always perpendicular to both magnetic field and particles' velocity. So this is interesting. At all points in time, it is perpendicular. That might not seem special until we get to tomorrow's lesson. So let's try an example. What is the direction of the magnetic force on a positive charge that moves as shown in each of the cases below? Okay, so I know you might not have color in your student notes package, but green is the velocity vector. So this is the velocity of that charged particle. If our velocity of our charged particle is down, we're gonna take our thumbs, we're gonna point thumbs down. Then you're gonna extend out your fingers. The magnetic field lines are pointing out of the page. So this is not the most comfortable, but do you see that your palm is pointing to the left? So your answer for this part A would be to the left. Then if we go to this one, so I always direct my thumb first because I find it's the easiest, but you can find your own, what works for you. So thumbs up, and then open up your fingers and make sure your fingertips are pointing to the right because we have the B to the right. So once you have your palm is like now pressing into the screen. So we would say into the page for part B. And then finally for part C, our thumb is pointing towards us. Our velocity of our charged particle is towards us. So it's like you're looking down your fingernail of your thumb. And then you're gonna open your fingers and your fingertips are gonna point towards the left. And you should see that your palm is down. So this is how I would write it up. In A and C, you could write an arrow or words. But for B, you really have to use words. You'd have to say into the page or use that convention of the dot being into the page. And write an FM because as you can see, it gets confusing. Like if you just write a dot, there's 3 different vectors that could be written as a dot. So you have to label them. Okay, let's try a longer example. In this example, an electron moves at a speed of 54 meters per second through a magnetic field with a strength of 1.2 Tesla. The angle between the velocity and the field is 90 degrees. What is the magnetic force on the electron? Calculate the gravitational force on the electron. What is the ratio of gravitational force to magnetic force? How would you answer for A? How would that answer for A be different if it was a proton instead of an electron? And how would your answer for A be different if the angle is 45 degrees? So just moving to that file. So first, a diagram. Let's say the electron is moving, let's say up, and the magnetic field, it says that it's 90 degrees to it, so we could do to the right or to the left. So in this diagram, just randomly gonna choose to the right. So it's given that it's 90 degrees, but I have choices. So what is the magnetic force on the electron? That's Fm. And our equation for Fm is QB sine theta. So the charge on one electron is 1.6 times 10 to the minus 19 now coulombs. I really hope you know that number now. I mean, you can always look it up. It's open book. The constant is given to you anytime you need it, or you are expected to know to look it up. But hopefully you do know that after the Millikan's oil drop lesson. V, velocity, is given to us in SI units. And the magnetic field is given to us in Tesla, and that's what we want. Now, sine theta, I didn't put it in here. Maybe I should. Sine of 90 degrees. What is that? Sine of 90 degrees. That is 1. So we don't need to put it in to get the right mathematical answer. When theta is 90 degrees, that's fine to not put it in because you know it's times 1. But just in case, you might want to just put it in, and you will get 1.0368 times 10 to the minus 17 newtons. And remember, we're reporting a forces vector. We need a direction. So we're going to use right-hand rule number 3. So looking at the diagram here, our diagram plus the words that we use are the answer. So you can't just say out of the page and not have a diagram because there's not enough direction here given. So thumb is going to point towards the top of your computer screen, and then you're going to extend your fingers, and you need to point your fingernails to the right. Do you see how your palm is pushing into the page? But it says that it's an electron. So what we really need to do is flip our answer so it's out of the page. So our final answer is 1.0 times 10 to the minus 17 newtons out of the page. Calculate the gravitational force on an electron. Well, we know gravitational force is mass times gravitational field strength, and we get 8.9 times 10 to the minus 30 newtons. So what A and B are just getting at is look at the relative size. So the force of gravity on an electron is much smaller, orders of magnitude smaller than the magnetic force. Part C asks, what is the ratio? So doing one over the other, well, it's the ratio of gravitational force to magnetic force. It's 10 to the minus 13 times smaller. Or you would say FG is 10 to the 13 times smaller, or you'd say FM is 10 to the 13 times bigger. Well, you could use the 8.6 if you should follow significant figures rules. How would your answer for A be different if it was a proton instead of an electron? It would be the exact same magnitude, but it would be into the page. So into the page. And then is there a part D? Part E. Part E says, how would your answer for part A be different if the angle was 45 degrees? We would have to put in sine 45 into the equation. So we're going to have the same diagram, but the velocity is going to be not 90 degrees to B, it's going to be 45 degrees to B. It's only the component of V that is in the direction of B that we care about. And so that's where the sine theta comes from. So we get 7.3 times 10 to the minus 18 newtons, and it's still out of the page because we're going back to talking about an electron. Okay, going back to our slides. Force on a current carrying wire. So we were talking about, it could have just been that Q. It's just a point charge and it's moving within a magnetic field. But there are many more examples in real life where we have not just one charge, but a bunch of charges flowing through a wire. The same concept applies, but we don't have Q, we have I, current. Remember, current is charges over time. So we're going to develop a new equation. A straight current carrying conductor in a uniform external field experiences a magnetic force due to the field. Magnetic force on a current carrying wire is equivalent to the sum of the magnetic forces on all the moving charges within the wire. So if I is Q over T, it's the sum of all of those Q. If you're interested in the derivation of this equation, it is in your textbook on page 393. The magnitude of the force in the wire can now be, we can use some substitutions for B and Q over T to get the force on the wire is current times length of the conductor times magnetic field strength times sine theta. We use right-hand rule number 3 to get the direction. Current, we're going to use, it's hidden here, but it's amps because that's the SI unit of amps, or of current, SI unit of length, SI unit of magnetic fields. Okay, so notice with sine theta being here, this slide exists whether you're talking about the previous formula or the current through a straight conductor. Sine theta, as you know, is it's a function of theta, and there are some times where the sine theta is 0. So if the angle between the wire and B is 0 or 180, or I guess 360, you won't have any force at all. So that magnetic force on the wire from right-hand rule number 3, that motor principle, that force associated with motor principle, that's only there if you do have an angle between the wire and B. In grade 11, we always did a 90-degree angle. So you could see sine theta, that was the maximum force. So the most noticeable force on a wire would be when it points 90 degrees to the magnetic field. Yeah, the direction of the magnetic field. If theta is 0, then we don't have a force. And the force is greatest at 90 degrees. So let's try an example. 2 electrical poles supporting a current-carrying wire. Oh, that's not a complete. 2 electrical poles are supporting a current-carrying wire. The mass of a 2.5 meter segment of wire is 0.44 kilograms. 15 amps current travels through the wire. The conventional current is oriented due east, horizontal to Earth's surface. The strength of Earth's magnetic field at the location is 57 micro Tesla. So micro means 1,000,000 times smaller than 1 Tesla, and is oriented due north, horizontal to Earth's surface. And the question is to determine the magnitude and the direction of the magnetic force on the 2.5 meter segment of wire, and then calculate the gravitational force. Okay. So first, drawing a diagram. It really goes a long way. So this, can't you see this is a vertical pole? I'm not sure why I drew it horizontally, but this is the vertical pole, and this is the east magnetic field lines. It says oriented due east. So, so we've got electrical poles, magnetic fields, there is a mass given, there is a length given, we have the current given, and we're told that the strength of Earth's magnetic, okay, so our B is given, current is given, mass is given, length is given. So can we find FM? Sure, we have ILB sine theta, we sub in our values. Now notice micro Tesla is not an SI unit, so we have to convert micro to Tesla by using times 10 to the minus 6. Then it says that the pole is vertical and the magnetic field is due east, so up is 90 degrees to east, so we know theta, and we can put in sine theta, or sine 90, which we know is 1. So 15 amps times 2.5 meters times 57 times 10 to the minus 6 Tesla, we get a force on the wire. Round to 2 sig figs. Now, force on the wire, we have to figure this out. So according to the diagram, if that was considered east and this was considered up, you would see that your palm points out of the page. So the force would be out of the page. And then for the second part, to calculate the gravitational force, we know gravitational force is calculated using the mass and 9.81. So this isn't written here, but if I just do it quickly on my calculator, you get 4.3164 newtons. So rounding it would be 4.3 newtons, and it would be down. Now you can see that 4.3 newtons is orders of magnitude bigger than the magnetic force. So that means if we have a 15 amps current, that pole is, the magnetic force is not going to be bigger than gravity. Okay, so time for you to do some practice questions. It seems like there's a lot of questions, but some of them are very quick. Some of them are just like an answer, positive or negative. Some of them are quick calculation. This leads very closely into the next day's lesson. So I just want to go back and add something. This was a photo at an instant in time that the charge was going downwards, and the force is always perpendicular to the direction of motion. But I just want to highlight that the instant that, like, this is a snapshot, but immediately after that force can act on that charge is going to move because of the force. That's what forces do. So it's pointing down at first, but as soon as we press play, if this was like a freeze frame of a video, we press play, that charge is going to turn because of the force. And now you have this as the velocity, and this is the magnetic field strength. And now it's going to further want to turn because the force is always 90 degrees to the velocity. This is how we get circular motion. Uniform circular motion is when the velocity is 90 degrees always to the force. So remember when we had like a yo-yo on a string, and we had that the tension was always towards the center, which is 90 degrees to the tangential velocity. So I just wanted to add this in as a transition into the next day's lesson, that right now, for 8.2 and 8.3, we're talking about the charge like traveling in a straight line, but that's only at a moment in time. And over time, you will get circular motion when the charge is free to be influenced by that force. So please make sure to submit this exit ticket for this video, and do and submit these practice questions. Have a beautiful sunny day and stay healthy. Bye-bye.